All right, this is our second example of a system of three equations with three variables. This is the one that when we looked at the graph, we found that it was dependent, that the three planes intersected along a line. But let's pretend we don't know that. We're just going to tackle it and see if we can figure out how to do it. For this one, I'm going to attempt to solve this using the elimination method. So looking at my three equations here, I'm going to see if I can eliminate x's and see where that takes me. So one of my equations has a 1x, which is pretty useful because I can take equation number 2 here and multiply it by whatever number I want on both sides, and that will change the coefficient of x to be whatever I need it to be to cancel out x's from other equations when I add them together. So in particular, let's start with equation 1. If I want to cancel the 5x's from equation 1, I can take equation 2 and multiply it by -5 on both sides. So let's begin with that. I'm going to take equation 2, multiply everything by -5, and get -5x minus 10y minus 5z equals -5. So all of the coefficients, all of the terms have been multiplied by -5. Let's take equation 1. I'm just going to rewrite it up here so that they are on top of each other to make it easier to do the addition. So now, adding those together, 5x minus 5x is going to cancel out. 8y minus 10y will give us -2y. And then z minus 5z will give us -4z. And that'll be equal to 10 minus 5, which is 5. So this produces a new equation. I'm going to call this equation 4 because it's kind of a new equation that I've got, which is I got it by adding equations 1 and 2 together. So we could replace either equation 1 or 2 by this new equation, equation 4, or we could consider it to be some new thing that we have that we can work with. So I'm just going to leave that for the moment, and we're going to do the same thing with equation 3. We're going to try to use equation 2 to eliminate the x's from equation 3. So let's see, I'm going to come down here and take my equation 2, and I'm going to multiply equation 2 by -2 so that I can cancel out the x's from here. So we have -2x minus 4y minus 2z equals -2. Everything multiplied by -2. So pairing that up with equation 3, which I'm not going to change. If I add those together, my x's will cancel. I'll have -4y plus 2y. So -2y. And then -2z minus 2z is -4z. And then -2 plus 7 is 5. Let's see. So that is, again, a new equation. I'm going to call that equation 5. So what I've done so far is I've basically used equation 2 to go and cancel out the x terms from equations 1 and 3 to produce 2 new equations, which I'm calling 4 and 5. This is not, by no means is this the only way to do this problem. There's so many different ways to solve a problem like this. It's really impossible to describe all of them. So I'm just showing you a particular strategy. And this strategy is going to kind of translate into that Gaussian elimination idea that I hinted at earlier. So now that I've got these two equations, 4 and 5, which have only 2 variables, y and z, I can take them together and see if I can figure out how to combine them and solve for my y and z variables. So I'm going to produce a new system of equations here using equations 4 and 5. And I'm going to write them both down. -2y minus 4z equals 5. And -2y minus 4z equals 5. Hey! Check it out. They're the same, aren't they? So if I were to add them together or subtract them or whatever, I would get 0 equals 0 again. This should look familiar, right? This is what happened with the our dependent example in two variables. So what this means is that we're going to be able to essentially pick one of these two variables to be a free variable, like we did before, and then try to get everything in terms of that free variable. So let me think about this for a moment. I think what I want to do is solve for y in terms of z. So let's take this negative 2y minus 4z equals 5 and solve for y. So I've got to add the 4z to both sides. So adding 4z to both sides will move it over from left to right. And now I can divide both sides by negative 2. And I'm just going to write it like this, 5 plus 4z, and then all over negative 2, like that. So y equals 5 plus 4z all over negative 2. So that's going to be one of my variable formulas. I'm going to replace the z with my parameter t. That's going to be my free variable, meaning it can have any value you want. So I have y in terms of z. Now what I've got to do is go back and try to get x in terms of z, because I want everything in terms of my free variable. So the easiest way to do that, I would say, is probably to go back to equation 2. Let's go pick equation 2 because it has this nice simple x, right? It's just one x. That's kind of handy. So what I want to do is solve this for x in terms of y and z. So I need to just subtract the 2y and the z from both sides, so I've shifted them over. So now I've got that solved for x, which is nice and easy. And then I'll do my substitution. So y equals 5 plus 4z all over negative 2 is going to substitute in right in there. So that's going to give us 1 minus 2 times 5 plus 4z over negative 2, and then minus z. In this instance, the negative 2's are going to cancel out, right? We have a negative 2 times negative 2 and divided by negative 2. So those are going to cancel, leaving us with 1 plus 5 plus 4z minus z. And then that simplifies nicely down to 6 plus 3z. Yep, that looks right. So here are the three things we need. We've got z is our free variable, it's t. Y is going to be, we have y in terms of z right here, so we can replace that z by the t. And we have x in terms of z right here, so we're going to be able to replace that z by a t. So, I ran out of space, so I'll just go like this. So my solution set is going to look like a set of ordered triples, right? We're talking about points in three-dimensional space with an x, y, and z coordinate. The x coordinate is going to be 6 plus 3, from here, 6 plus 3t. I'm going to use my parameter now instead of the z variable. My y is going to be 5 plus 4t all over negative 2. And then my z is just t itself. And so there I have the format of the solutions. Any point which is determined by these formulas for any value of t, right? This is where t is any real number. Any of those points would be solutions to this equation. And this set notation here describes that entire infinite set of points along that line of intersection all in one go. So that's our solution set.